Thanks for dialing into this webinar. Today I'll be discussing the subject of waterside heat recovery. My name is Mike Jenin and I work at AIR, and we are a manufacturer of specialized heating cooling equipment. I describe them as experts at refrigeration and experts at compressorized HVAC equipment. My role is servicing Canada and coming up with new innovative ideas that are unique for our climate. As most people know, Canada is cold most of the time and our climate is heating dominated. As a result, the subject of today's webinar is heat recovery chillers. This technology has become popular over the last few years as a method of energy savings, but it is not a new technology. Many older buildings right here in Toronto have always used low-grade heat from chillers as a method of heating. And then in the 80s and 90s, natural gas became popular, it became cheaper and the preferred method of heating. But now, due to rising energy costs and the need to reduce greenhouse gas emissions, the demand for heat recovery has increased. We will talk about what heat recovery is, the economics behind it, and then move on to the obstacles of heat recovery, and I'll show real examples of how it can be implemented. Cold climates require a lot of fossil fuels, which are used for heating. Space heating and hot water heating account for 70% of the total energy use in residential and commercial buildings. Typically, these are derived from fossil fuels. The role of heat recovery is to offset a portion of this heating demand, by doing so saving money and reducing greenhouse gas emissions. Many countries, provinces, cities have similar greenhouse gas plants. You might hear something along the lines of a 30% reduction by 2020 and an 80% reduction by 2050. The federal government of Canada has broken out where the expectations are in terms of reductions by sector. We start with 815 megatons as the total currently, and then each sector is responsible to reduce by a certain amount until we hit our target of 511 megatons. Aside from future reductions, which is essentially a catch-all for a whole bunch of different things, buildings are accountable for the single largest contributor when reducing future greenhouse gas emissions. In the past, the more obvious culprit for greenhouse gas emissions was transportation. When we talked about greenhouse gas emissions, we always showed a photo of cars sitting in traffic on the highway. But what's interesting about this graph is, according to future reductions, buildings are accountable for more than twice the reductions moving forward than the transportation industry. So moving in the future, greenhouse gas emission scrutiny will be focused on buildings, and heat recovery will play a large role in helping us get to our target. Looking at a conventional HVAC system, we literally throw heat out the window. In this case, the window is the cooling tower. The gas boiler maintains the heat load, an electric chiller provides the cooling load, and the chiller is rejecting heat outdoors with this cooling tower. The gas boiler is consuming 56 cubic meters per hour of gas in this example. The electrical chiller has an input, and so do several miscellaneous devices such as the cooling tower fan motor and the condenser water pump. When added up, this system consumes about 83 kilowatts of power. Essentially, we are cooling the building and dumping the heat outside. Then we are using fossil fuels to regenerate this heat again for heating. Heat recovery. The process involves capturing this otherwise rejected heat and using it for the heating process. In this simplistic example, all of the heat from the chiller is recaptured, known as a simultaneous load. Typically, while the amount of heat rejected by the chiller is plentiful, it's at a very low grade temperature. Cooling towers operate at 95 degrees Fahrenheit. The chiller needs to work harder to increase the temperature of the condenser, consuming more electricity to upgrade heat. In this case, 144 kilowatts. The cooling tower and other miscellaneous devices are turned off, and the boiler is also turned off. However, this results in a 28% reduction in operating costs and a 95% reduction in carbon emissions. Note this is using Ontario utility rates. This is looking at the simultaneous load only. In most buildings, there will still need to be a certain amount of excess cooling or excess heating, which cannot be derived from heat recovery. However, we've demonstrated that the simultaneous load, at least, it's more cost efficient to recover heat than it is to produce new heat, even though fossil fuels are relatively inexpensive. No building has a perfect simultaneous load. To demonstrate this, I've drawn this theoretical heating and cooling load profile. The cooling load is in blue, with the peak cooling near the center of the graph representing 500 tons. And the heating load is shown as red, with the peak being at the ends of the graph representing wintertime. As you can see, these loads are not the same, but there is always at least some kind of simultaneous load. This shaded in blue region represents the simultaneous load. This is the total available energy for heat recovery. The most energy efficient case, or if we're looking for the largest greenhouse gas reductions, would be to size the chiller for the peak simultaneous load, 200 tons in this example. The system would not always operate at full load, but it would have a larger capital cost. The energy savings would be the priority, and this would be the way to go. The total annual energy savings would depend on the exact load profile. However, if we wanted to size the chiller for the maximum ROI, then we would size the chiller for the maximum continuous load, 100 tons in this example. This would be considered the most cost-efficient sizing of the heat recovery chiller, as it decreases the size of the machine and allows it to run at full load all of the time. This would yield an annual savings of $60,000 per year in energy costs. If we implemented a 100-ton heat recovery system in this instance, the remaining cooling load profile could be reduced from 500 tons down to 400 tons. This remaining 400 tons of cooling can be done with a downsized conventional chiller. This is because we can rely on the minimum base cooling load of 100 tons, which has been offset by the heat recovery chiller. It's best to size the cooling system as a whole and take these considerations into account in order to achieve the greatest ROI. Some might say that these numbers look great for a lower water temperature of 135 degrees in this case, but what happens at a hotter water temperature? Doesn't the efficiency decrease, resulting in a poor ROI? So I prepared this graph of the hot water temperature and operational savings. This is for a 100-ton chiller. Generally, the efficiency of the system decreases with an increase in hot water temperature, and as such, the operational savings diminish. This relationship is mostly linear, with the exception of very high water temperatures, with, in this case, 170 degrees being the upper limit for most chillers. And this limit is a function of refrigerants and the compressors used today. The efficiency tapers off at this high temperature, and in fact the operational savings become negative, which means that the heat recovery system is more costly to operate than a conventional system. However, you might have other factors to consider on a project such as greenhouse gas emissions, but certainly up to 160 degrees, heat recovery systems operate more effectively and have a lower operating cost when compared to conventional systems. This chart can be used as a quick guide to estimate the feasibility of a project. For example, a 200-ton system with 140 degree supply temperature would have an annual savings of about $100,000 per year, given that this graph is for 100-ton increments. We can then compare that to the expected capital cost of the project and quickly determine the feasibility of the project. What about greenhouse gas emissions? Using waterside heat recovery can be used to offset the use of natural gas. Since heat recovery chillers are driven by electric compressors, we need to look at the carbon footprint of the electric grid. What we find is the emissions due to electricity vary greatly across the country. Most numbers are based on Ontario utility rates for the purpose of this presentation, and Ontario has a relatively clean electric grid. When most people think of reducing greenhouse gas emissions, they might think of solar, PV, wind, or some other green technology that's used or added to the building to generate new energy. But as it turns out, the most green thing you can do is to recover the heat energy you already have. Efficient condensing gas boilers, for example, here's how the numbers turn out. The system costs $30,000 and it will produce about 55 kilograms of carbon emissions per 1 million BTUs of heat. Solar PV, as a comparison, per million BTUs of heat would have a capital cost of $439,000 and they would emit about 14 kilograms of carbon. This assumes no capital costs associated with an electric HVAC system required to derive the solar heat. This is just for the solar panels. Obviously, solar panels don't emit any carbon at the installation site, but this is a life cycle carbon cost. And then we look at a heat recovery chiller, which per million BTUs emits between 3 and 5 kilograms and would have a capital cost of about $148,000. One thing to note is that this is looking at the heat produced only. It doesn't include the carbon offset from the otherwise produced cooling that the heat recovery chiller would provide. Since Ontario has a clean electric grid, the carbon from the electric cooling wouldn't be that much. But in high carbon regions, the heat recovery would emit more carbon because it's using electricity from a high carbon grid, but it would also offset the use of an electric chiller from also a high carbon grid. So that's something to take in consideration. Also to note, the range in carbon emissions from the heat recovery chiller is mostly dependent on the COP you achieved, which is mostly dependent on the design hot water temperature as we illustrated. In most cases, the heat recovery chiller has a lower carbon footprint and a lower installed cost. It doesn't mean that it's always better than solar PV, and no one should ever use solar PV. But what it does mean is that if you have a relatively clean electric grid, your first line of defense for future greenhouse gas emissions should be heat recovery. So if heat recovery is so great, why hasn't it been implemented everywhere? Here are the top obstacles of heat recovery, and moving forward with the remainder of this presentation, we'll talk about examples and how to overcome them. And I'll also use some real-life case studies as illustrations. So the first is no simultaneous load. This means no opportunity for heat recovery. Many buildings will not have a simultaneous load all of the time, but all buildings will have at least some kind of simultaneous load, even if it's extremely intermittent. Fine, we have a simultaneous load, but it's extremely intermittent. There is some load, but it doesn't happen all of the time. A good example of this would be domestic hot water. Perhaps a larger residential building with a heating, cooling changeover system, but during cooling, there is still domestic hot water use. Here is an opportunity for heat recovery, and I'll cover this in some examples. Heat recovery chillers can't develop a hot enough water temperature. As heat recovery became popular, chiller manufacturers would adapt comfort cooling chillers and try to force them to do heat recovery. There wasn't much of a mechanical difference between a regular chiller and a heat recovery chiller. Most manufacturers used, for example, R410A as a refrigerant, which is limited to about 120 or 130 degrees in terms of its hot water production. But this is not hot enough for supplementing, especially older buildings with non-condensing gas boilers that need to operate at 160, even 180 degrees. Now, heat recovery chillers are readily available that go up to 160 degrees and in some cases above 170 degrees. The additional piping for the chiller is too complicated. There are many different ways to implement piping for a simplistic installation. Last thing you want to do is spend money on a heat recovery chiller for it to only cause extra maintenance and operational headaches. I'll go through several examples of piping and how it can be simple. Finally, the additional control sequences are too complicated. How do we control this heat recovery chiller to get the maximum amount of heat? Most heat recovery chillers have their own internal controls, but there are still considerations for the overall system design that can make these systems very complex or very simple, and I'll cover that as well in these examples. The most simplistic example, a dedicated heat recovery chiller. A dedicated heat recovery chiller offers full control over the condenser hot water temperature. Since it's sized for the hot water load, it will always be able to maintain this load as the heating load ramps up and down. The chiller will not be able to control to the cooling load. If the cooling load disappears, the chiller can watch for this and unload its compressor. However, in that scenario, the amount of heat available will be reduced and eliminated. The key takeaway is the chiller can watch both hot and chilled water sides, but it can only control to one of them. And it can only control to the lesser of these two loads. If the heating load is low, it will control to this, and it will not be able to keep up with the cooling load. If the cooling load is low, it will control to this and it won't keep up with the heating load. In most instances, you don't have a perfect simultaneous load, so additional measures are required. Here's a slight modification and a more realistic scenario. The cooling load is consistently larger than the heating load, or perhaps we've chosen to only tackle a small portion of the heating load. We have 150 tons of cooling in total that we've chosen to install, but we've only taken a 50-ton heat recovery chiller in this case. We've chosen to pipe this chiller in a side stream configuration upstream of the main large chiller. The return chilled water pipe will be pre-cooled by the heat recovery chiller. This makes sense if your heat recovery chiller is small compared with the main chiller, or if you only have access to the return chilled water line. It's also an excellent choice for retrofit applications as well. This heat recovery chiller is dedicated to serving the hot water load. The cooling load is much larger than this chiller could ever supply, so the remainder of the chilled water load is made up by the main chiller. This results in simultaneous temperature control of both the hot water and the chilled water. One thing to note is if the heating load would disappear, the heat recovery chiller is unable to operate. It has no way to reject its heat without a heating load. The cooling load in this case must be completely handled by the main chiller. Hence, we have a total cooling load of 150 tons, yet we have a total installed chiller capacity of 200 tons. This is something to consider when you calculate the ROI. In most instances, it won't matter if the main chiller is an existing machine. Here is an example of a side stream chiller. In this case, the unit recovers heat for a single air handling unit. Chilled water connections are in the midsection and are connected to a large existing main chiller plant. Hot water connections are near the bottom as they're connected to the red air separator. The chiller runs and the compressors are controlled to the leaving condenser water temperature, which is the supply to the air handling unit. We are confident that there is a cooling load year-round, and therefore we will always have a source to recover heat from. These examples are fairly simple, but what happens if your loads are intermittent? Is it still worth implementing heat recovery? This is what I would call a hybrid system. The chiller is designed in such a way that it can provide both the heating and cooling loads. The chiller controls to the cooling load. Heat is recovered for the heating process. If the heating load is satisfied, then we need to reject this waste heat elsewhere. Otherwise, the chiller will be unable to operate. This typically means the implementation of an auxiliary heat rejection method, such as a cooling tower in this case. Well, this could be done by switching over some hydronic piping, valves, and a heat exchanger. This chiller has the ability to be connected to both the heating load and a simultaneous auxiliary heat rejection device. It can automatically control to the hot water temperature and maintain the heating load by modulating how much heat is recovered between the two loads. Here's an example of what this looks like as a real installation. Here there are two chiller modules in this case. Both modules are connected to the cooling tower as their primary condensers. This is shown there off the photo at the bottom. And the chiller towards the back has a secondary condenser for heat recovery. In this case, this condenser is fed by the green pump, which supplies a boiler system used for domestic hot water. Domestic hot water loads are very intermittent, and this chiller has the ability to direct its hot refrigerant between the cooling tower loop and the domestic hot water loop. In terms of controls, the hybrid system is very simple. The chiller controls the chilled water load like any other chiller. The heat recovery chiller has a temp sensor in the boiler loop. When the temperature drops below set point, the chiller begins to modulate hot refrigerant to the auxiliary condenser and starts the circulation pump to reject the heat to the boiler loop. Essentially, it acts like another boiler. Another implementation of hybrid heat recovery, in this case, the load is still 150 tons like we showed in the previous example with the main chiller, but we've installed a secondary condenser on the third chiller module furthest to the right. In this case, the heat recovery load is small and served only by this third chiller. However, it could be set up that all three chillers have the hybrid heat recovery feature. In this case, the first two chillers on the left are rejecting heat to the cooling tower only, and the third chiller has the ability to reject heat to either the cooling tower or the heating load. In this instance, the cooling load is 150 tons, but unlike before, we have an installed capacity of only 150 tons rather than 200 tons like with the main chiller. This is one of the benefits of a hybrid system. Because it can reject to either the cooling tower or the heating load, you can count on its capacity even when the heat load becomes intermittent. You're not paying for a 150-ton main chiller plus an additional heat recovery chiller. You're only paying for a total installed capacity of 150 tons. Here's a photo example of such a chiller. In this case, it's being tested at the factory. In this scenario, there are actually 4 chiller modules. 3 chiller modules are cooling only, and then the last 4th module has an auxiliary condenser specifically sized for the hot water load. The cooling capacity of the 4th module counts towards offsetting the total cooling load, since the unit can switch between rejecting heat to the cooling tower and recovering heat for the boiler loop. There are also air-cooled examples as well. An air-cooled chiller makes this hybrid model very simple because the auxiliary heat rejection can be completely controlled by the chiller itself. There's also no cooling tower or condenser water piping. Since it's one packaged unit, with these chillers, all you need to do is bring your chilled water lines like any other machine and bring in your hot water lines like any other boiler. This makes for an extremely simple install and extremely simple controls, which are all contained inside the chiller. The chiller can alternate between generating hot water or rejecting heat out through its built-in air-cooled condenser. And here's a photograph of an example of this type of chiller. You can see there are 4 water connections. The 2 connections at the rear are the chilled water connections, and these 2 connections at the front are to be piped to the hot water heating system. So now we'll take some questions and wrap up the presentation. A couple questions. Can the chiller be reversed to act as a heat pump? The short answer is yes. A lot of instances it's common for the air-cooled chiller. This goes beyond the scope of heat recovery, but the air-cooled chiller can act in chiller mode, heat recovery mode, and then have an air source mode. So if your cooling load disappears in wintertime, let's say, the chiller can still provide some level of heating by extracting heat out of the ambient air. What is the maximum hot water temperature? Well, it depends, like I alluded to earlier. Most chillers can produce at least 160 degrees if they are designed for heat recovery. In some instances, 170, 175 degrees. If you're using the correct refrigerant and if you're using a compressor type that is suitable for that amount of lift. What is the cost of a heat recovery chiller compared with a conventional chiller? This is a good question. So in terms of the actual mechanical chiller itself, there's not much of a cost difference between a normal chiller and a heat recovery chiller. The heat recovery chiller produces 100 tons, let's say in normal cooling mode. It's roughly the same cost of a normal chiller. But what happens is when you go in heat recovery mode and you want that higher hot water temperature, let's say 160 degrees, the amount of power or horsepower or the amount of chiller you need at 160 degrees, it almost doubles. So to get the same amount of cooling out of a heat recovery chiller at 160, you would essentially need double the horsepower of chiller, and that would have a cost that is about double. If your design temperature is a little lower, you need less horsepower of chiller, the cost is less. So it really is heavily dependent on the design water temperature. What about a water-side economizer? This is a question that gets asked all the time. Is it better to run heat recovery in winter to produce heat, or is it better to run a water-side economizer? Essentially, you would shut off the chiller or cooling and use the water-side economizer to produce the cooling. Then whatever heat you need, you would run your gas boiler. And the answer is it's typically more efficient. Even if you're getting the cooling for free, the COP of a heat recovery chiller is typically at least the same operational cost, or if not better than a natural gas boiler. Depends on your utility rates, but it's typically better to recover heat than it is to throw the heat out the window, even if the cooling is still free. How much lift can the heat recovery chiller provide? So this means what's the hottest temperature versus the coldest temperature in the evaporator on the cooling side. This is heavily dependent on the compressor technology to use, but it's not certainly out of the realm that a heat recovery chiller can provide, let's say 10 or 15 Fahrenheit chilled fluid and 160 degree heat recovery. It will vary from manufacturer to manufacturer. It will be a function of what refrigerant they're using, and it will also be a function of the compressor type they're using. So that concludes the presentation. In summary, I hope I've showed several examples of how heat recovery can be profitable and good for the environment. I have plenty more examples and variations of these systems as well, so feel free to reach out to me if you have any other questions or need more examples for your application. And thanks, and have a great day.